So I wanted to show you another example of a induction proof that also has to do with derivatives. And what I'm going to do is first figure out what exactly I'm trying to prove and then use induction to prove it. And so what I'm going to look at is a function that's a great example here, that we have a function that is called the natural log of x. And if you remember that the derivative of the natural log of x, it's kind of weird because it seems like it changes into a completely different type of function. The derivative of the natural log of x is 1 over x, which if you rewrite that as power, it makes it easier for you to then take the next derivative. So the second derivative of the natural log of x is going to be negative 1x to the negative 2. Third derivative is positive 2x to the negative 3. Fourth derivative, I'm just doing the power rule over and over again. And I hope you're noticing some sort of pattern here. The numbers in the front are switching back and forth from positive to negative to positive to negative. I can even include a 1 right here on the first derivative. So I have positive, negative, positive, negative. The other thing that's happening is they are multiplying. As we count up, they're multiplying. And so that makes me think of a factorial. And the power is just counting up in the negatives or counting down, depending on your perspective. So the claim that I'm going to make is that the nth derivative of the natural log of x is equal to, I might have to come back through and fix this, negative 1 to the first, or negative 1 to the n. That's what we usually use for switching back and forth. I'm going to double check that it works here in a second. N factorial. Again, I'm going to double check that that works here. And then x to the negative n. Now, I think I got to fix this up because I'm noticing that the first derivative has a positive, right? And then it's a negative, and then it's a positive. So that means that when n equals 1, I need it to be a positive. So I'm going to go through and fix that. I'm going to make this n plus 1. Because when n equals 1, then n plus 1 is 2, and negative 1 to the second is positive. When n equals 2, n plus 1 is 3. I could have also done n minus 1. The same thing works. I'm also noticing, I think that my factorial is off because the second derivative has 1 in front of it, the third derivative has 2 in front of it, the fourth derivative has 3 factorial in front of it. So it looks like this is n minus 1. And maybe it makes a lot more sense for me to make the exponent also be n minus 1, although it doesn't really matter. I could prove it either way. They are equivalent. But I'll just make it consistent, n minus 1. So let's go through the 3 steps of induction then. So first, we have our base case. The first derivative, which I guess I should just write as a prime, but that's okay. The first derivative is equal to 1 times x to the negative 1, because I showed that right here. And that's also the same as if I did negative 1 to the 1 minus 1, 1 minus 1 factorial, x to the negative 1. And that works because this is equal to 1. This is equal to 0 factorial. 0 factorial is equal to 1. We're good. Checks it out. Second is I assume this. So I'm just going to copy it down there. Assume. You're just assuming it for the sake of argument. Then the third step is to consider the n plus 1th derivative. And the n plus 1th derivative is going to be the derivative of what you assumed. So I'm going to take one more derivative. But what I want you to notice is this looks complicated. There's n's and x's, and now there's these d's, and it's a lot. But what I want you to recognize is that this is a constant, this is a constant. This is really just number x raised to the number. You know how to do that derivative. It's the power rule. You just go multiply the exponent in front, and then subtract 1 from the exponent. So what do we have? We have negative n, that's the power going down in front, all the other constant junk there, subtract 1 from the power. Then I'm going to clean it up. Negative n is the same as negative 1n. So I'm going to bring like factors. Negative 1 times negative 1 there means my exponent goes up by 1. So my exponent becomes negative 1 to the nth power. N times n minus 1 factorial. Well, n minus 1 factorial means count down and multiply. And now I just brought term n in it. That's at the top of the line. So n times n minus 1 factorial is just n factorial. And the power of negative n minus 1 can be written like this, negative n plus 1. And if you go back to your original claim and you iterate it one step in the future, n minus 1 becomes n minus 1 becomes n becomes n plus 1. We proved it by the principle of mathematical induction. So that's an example that kind of blends some of the derivative ideas together with the induction ideas that we've been working on. So reach out. Let me know if there's anything I can do to help. Thank you.